Alright, so this is part 2 of area and definite integrals. And basically we talked about the number of rectangles as they get larger and larger. We can actually get closer and closer to the approximation of what's underneath the actual curve. And what we're going to be talking about is the limit as n approaches infinity. So in other words, as we get to an infinite amount of triangles, what are we actually getting to? And we're actually approaching the area under the actual curve. Okay, but I want to take a look at the formula real fast. Alright, so real fast, the height and width are the formulas we need for the formula of each triangle. So the height would be f of x, and the width would be delta x. Okay, so that's pretty simple. Alright, but here's the thing, is the delta x is actually approaching 0, because the more infinite triangles or the more rectangles we get, we actually get in there. So this number is actually approaching d of x. Okay, and that's where the d of x actually comes from. Alright, so when we're doing definite integrals, okay, this becomes something different. So this whole formula right here will actually turn into something that looks like this, that we've seen before. Pretty cool, huh? And this would be okay. Alright, now the f of x would change, would definitely be changing each time, but it would still be the same. But then the d of x, which would be approaching infinite, would be looking like this. Okay, now what we want to do is we want to actually have it be a certain number. So we would call this the upward bound, and this one be the lower bound. Okay, and this is actually how we all set it up. Okay, so that's where we get that notation from. It just works across. Now there are complicated proofs to actually prove why delta x turns into d of x, but I'm just going to leave that to you to go ahead and figure out. Okay, but here's the cool thing, is that this is basically an integral. And what we're going to do is you're going to take the upper bound, okay, f of b, okay, and you plug that in, and you're going to minus capital F of a. Okay, so in other words, you find the integral of the actual function, and this is really kind of cool how this transforms from a rectangle all the way to dealing with the function and just working with it. But if you think of it, the height of every single one of these rectangles is the y-coordinate, and the y-coordinate is the function, the f of x. So that's how we can actually transform this into an actual problem of just finding the height of each rectangle. And it just works just beautifully like this. So here's the really cool thing. You don't even need the picture to actually work with definite integrals. Basically all you need is an upward bound. So let's say all 2, 4, 4 from 2 to 5 of, let's say, 3x squared minus 4x dx. Okay, so our original function is, so our height is going to be 3x squared minus 4x. Our width is dx. All we need to do is actually just find the derivative of each. Okay, and so here's how I actually have learned to write it. So in the past, I've done this. I've had this set up like this, to where I have the 5 and then the 2. You're going to learn a whole bunch of different ways to actually write this and just work with it. Well, actually, no, I'm sorry. Let's get rid of that. Boom. Get rid of that. Boom. Let's get rid of this. Delete. Okay. Let's actually get the actual thing in there. Okay. So what we would do is find the actual integral. Okay. So the actual integral would be x cubed minus 2x squared. Now in this case, since we're doing a definite integral, here's an interesting process. Watch this. I'll have the plus c in there like we just talked about, and then I have this right here. You have this at the end to connotate the numbers, the 5 and the 2. So we still need to do the 5 and the 2. So what I'm going to do is, if you notice, I'm going to plug 5 into the first one. So this is going to be 5 cubed minus 2 times 5 squared plus c. We don't know c, but then we're going to minus 2 cubed minus 2 times 2 squared plus c. Okay. Now, if you notice, here's the really cool thing. We're going to have a plus c here, then we minus another plus c. Basically, you don't need to have c's in your final answers of definite integrals. So definite integrals, you do not need the c's because they're always going to cancel out. All you need to just deal with is just the numbers. So this turns into 125. Let's go 125 minus 50 minus, what is that, 8 minus 8, which is really interesting. That turns out to just be 75 as the actual area underneath this curve from 5 to 2. Okay, and so that's the really cool part about this. And let's see in Desmos what we actually did. Okay, so here's my actual function, 3x squared minus 4x, and I have the lower bound being 2 and the upper bound being 5. So I actually found the area of this region right here. Okay, this region, and also above the x-axis. That goes without saying. Okay, all right, but that's pretty much it for just visualizing what exactly went on, and I actually found that to be actually 75 square units. Okay, so without further ado, ladies and gentlemen, that is how you work with definite integration. You just take your time and you just work with it, and you just be very careful with it. You just find an upward and a lower bound. All right, let's take a look at another integral. X squared, the definite integral from 0 to 2 of x squared plus 1 dx. Okay, so first off was we do the actual definite integral. We go 1/3 x to the third plus x. Okay, and then we have our notation at the end. And we put the 2 here and the 0 here. Okay, all right, and then what we do is the upper bound part first, which is going to be the 1/3 times 2 squared plus 2, and then we're going to minus that. And once again, I'm ignoring c because we're doing definite integrals, and the c's will cancel out at the same time. So we got the 1/3 times the 0 squared plus the 0. Okay, and as you can see, this is going to turn out nice and neat, pretty much. Okay, so this second part's just going to become 0, so that's really, really nice. Okay, but this, oh geez, what am I doing? I'm not even paying attention. This should have been a third. Whew. Boy, oh boy. And this should be a third as well. To the third power is what I'm saying, not a third, actual third. Okay. Alright, and so this is just going to become, let me see. Oh, this should stay 2. This should turn into a 3. Okay, so this is going to stay as 8/3 plus 2 okay, and that's going to turn into, what is that, 14/3, and voila, there you go. You're actually able to find the actual definite area underneath this curve from 0 to 2. Now, if we had a different number from 0 to 3, that would change the numbers, because now we're increasing this to 3 cubed. This, if we increase this from 0 to 1, this would also change how much of a lower bound we cut off. Now, oh, you know what? Let me go back. The reason why we kind of do the upper bound minus the lower bound, I didn't talk about that as much. The reason why we do the upper bound minus the lower bound is the upper bound, okay, so this is our entire area here, okay, and this right underneath here is the lower bound. So if we do the upper bound, which is this entire thing, minus this lower bound, we actually get this area right in here. So that's why we do an upper bound minus a lower bound, okay? All right, let me get another problem. Okay, so now we're going to find the integral from -3 to 1 of 6x squared minus 5x plus 2. Okay, so first off, you always, once again, you find the actual integral of that, and that is going to be 2x cubed, and I promise I'm paying attention to the cube now, minus 5 halves x squared plus 2x. Then we have our notation for the end of the integral before we start plugging in stuff. So 1 and the -3. Okay. All right. Now in these ones, you're going to be plugging in. If you notice, I'm going to be using -3 instead of just a positive number. So this is going to be 2 times -3 to the third power minus 5 halves times, well, -3 is definitely going to be a 9, so that's going to become 9 squared. Well, in actuality, this should probably become -27. Okay. All right, and then minus 6 is going to be the last part of it, and then we're going to minus. Oh, that's all the second. That is the second part. Okay. All right. So the first part. Sometimes I accidentally do the first part first, the last, and then the second part first. Okay. So the first part is going to be 2 times 1 cubed, which is 2 times 1 cubed is 1, minus 5 halves times 1 squared, which is 1, then plus 2, then we'll minus those together. Just work our way across. Okay, so this part's going to be kind of neat. So this will actually turn into 2 minus 5 halves plus 2, and then we minus a -54 minus 45 halves minus 6. Okay, and this will all turn into a positive 84 amazingly. Okay, now for some of you guys, you're probably going to get, sometimes you will get a negative number. Okay, and that happens sometimes. Just be ready for it when you're working with it. It's okay to get a negative number, and that just means your area is underneath the x-axis. Okay, so if this turned out to be -84, that would just mean the area is underneath. Okay. Alright, that's it for areas and definite integrals part 2. I'll talk to you guys later. Just take your time and just do work. Okay, bye.